This workshop explains how the fidelity of audio equipment is assessed and measured. I believe many magazine and online reviews fail their readers by glossing over performance specs, instead using subjective wording that's mostly meaningless. For example, what's a forward sound or a sterile sound? What defines a musical sounding preamp? How can a subwoofer have fast bass? Even when product specs are given, they're often dumbed down. A loudspeaker review might state the size of the woofer, but not its low-frequency cutoff, which is much more important. Or the cutoff frequency is given, but without stating how many dB down it is, or how quickly the response rolls off below that frequency. Some vendors provide incomplete specs. They'll tell you the distortion of the power amps in a powered monitor, but not the distortion of the speaker drivers, which of course is what really matters. This workshop will describe the specs needed to properly assess the fidelity of audio devices and explain what they mean using plain English. Hopefully this will encourage manufacturers and reviewers to be clearer and more thorough when describing the fidelity of audio products. We'll also explain why measurements are a better way to assess fidelity than listening alone. So why should we care about specs? Can't we just listen to audio gear to know if it's any good or not? I see audio specs as a consumer tool. They're just as important as knowing miles per gallon for a car purchase or lumens output versus watts consumed for energy-saving light bulbs, or even the fire rating for children's bedclothes. We're entitled to know what we're getting for our hard-earned money. In my opinion, just listen is not sufficient because there are so many variables and too many situations where higher levels of distortion might be missed. Yet some people believe that listening alone is adequate to assess audio fidelity. In the early 1980s, I designed and built a large professional recording studio, and I dabbled as an amateur circuit designer. I built a number of audio devices, including parametric equalizers, microphone preamps, 3 analog synthesizers, and even this entire mixing console. I also designed this distortion analyzer featured in my column for Recording Engineer Producer magazine. Of all the circuits I built, I can't recall one that measured well but sounded bad. However, the opposite happened early in the 1970s when I was still learning. I had designed a self-adjusting third-octave graphic equalizer, the first such device I'm aware of, and it sounded fine to me. But when I approached Irv Joel, a prominent audio retailer at the time, to help market it, he told me he measured 2% intermodulation distortion. That was an important moment for me because I learned that hearing is not absolute. Just because something sounds okay on some types of music doesn't mean it really is okay or that it will sound good with everything. One common myth is that fidelity is not fully understood, so two devices may measure the same yet sound very different. This is not true. Of course, you have to measure everything and at different volume levels. Measuring harmonic distortion at 1 kHz at a nominal volume is insufficient because distortion often increases at low frequencies and high output levels, especially with gear that uses tubes and transformers. But if you run a comprehensive series of measurements and get similar results, say within 1 dB, you can safely conclude that the two devices probably sound more alike than different. Another way to confirm that modern test methods are complete is with the null test. A null test subtracts two audio signals to see what remains. Subtracting is done by reversing the polarity of one source, then mixing it with the other at exactly the same volume level. If the result is silence, you can be confident that both sources are identical. Further, if a residual signal does remain, its level shows the extent of the difference. You can assess the nature of a residual signal either by ear or with an FFT fast Fourier transform analysis as shown here. For example, if one source has a slight low-frequency roll-off, the residual after nulling will contain only the low frequencies that are affected. And if one source adds a strong third harmonic to a sine wave test tone, the difference will contain only that added content. Nulling has been used to measure distortion since the 1940s. More modern analyzers can measure everything that affects fidelity with great precision at levels far softer than any human can possibly hear. If there really was some aspect of audio fidelity that science was unaware of, it would have been revealed years ago by nulling. I'll also mention the RAIN library, which has many excellent articles about measuring audio fidelity. Perhaps the most important spec of all is price. Thankfully, even budget gear these days is a lot better than what old-timers like the guys on this panel used back in the 1960s and 70s. But still, I believe that vendors and magazine writers do us a disservice when they minimize specs and reduce reviews to, "It sounded good to me." However, there's a difference between high fidelity, accuracy of reproduction, and a pleasing character of sound. The former is easily measured, but the latter is subjective and must be assessed by listening. There's also a difference between creating pleasing tones in a studio and reproducing a finished mix where accuracy is the best policy. The mixing engineer is responsible for making the music sound good using every means possible. But thereafter, high fidelity is needed to maintain that sound until it reaches the listener's ears. So while you can't measure a listener's enjoyment, you can absolutely measure and specify the fidelity of audio gear. My last AES workshop in 2009 addressed audio myths and also described the 4 audio parameters needed to define fidelity. I won't belabor those parameters in detail again, but I'll mention them briefly since they're at the core of this discussion. My previous AES workshop is also available as a video, and it's linked in the description for this video. By definition, high fidelity means how faithful a copy is to its source. Only 4 parameters are needed to define everything that affects the fidelity of audio equipment: noise, frequency response, distortion, and time-based errors. Noise determines the softest level that can be captured in a recording. With modern digital systems, the background hiss is much lower than the ambient room noise picked up by the microphones. Subsets of noise are AC power hum and buzz, vinyl record clicks and pops, left-right channel bleed-through or crosstalk, and even doors and windows that rattle and buzz when playing music loudly. Frequency response describes how uniformly an audio device responds to various frequencies. Errors are heard as too much or too little bass, mid-range, or treble. Subsets of frequency response are mechanical resonance, acoustic resonance, and electronic ringing, such as boosting a parametric equalizer using a high Q setting. Distortion is more technically called nonlinearity, and it adds new frequencies not present in the original source. Nonlinearity occurs when a circuit amplifies some voltages more or less than others, which changes the wave shape. Nonlinearity can flatten waveform peaks, as shown at left, or create a level shift called crossover distortion as the wave passes through zero, as at right. Peak compression occurs when electrical circuits and speaker drivers are pushed to levels near their limits. There are 2 basic types of distortion, harmonic and intermodulation, and both are caused by the same nonlinearity, and so they always occur together. Intermodulation distortion requires 2 or more frequencies to be present, and it creates new sum and difference frequencies. IM distortion is generally more audible and more damaging than harmonic distortion because the added frequencies are not always related musically to the source. I'll address this in more detail soon. Time-based errors affect pitch and tempo. When the hole in a phonograph record isn't perfectly centered, the pitch rises and falls with each revolution. That's called wow. Analog tape recorders have a related artifact called flutter that's much faster and adds a warbling effect. The timing error in digital devices is called jitter, but the frequency change is so rapid it manifests as noise or distortion rather than vibrato. When assessing fidelity, these 4 parameter categories are all we need for any audio gear. Although published product specs could tell us everything needed to evaluate a device's fidelity, specs can be incomplete, misleading, or even fraudulent. This doesn't mean specs can't tell us everything. We just need all of the data. However, getting complete specs from audio manufacturers is another matter. Often you'll see frequency response given, but without a plus and minus dB range. Or a power amp spec will state harmonic distortion at 1 kHz, but not at higher or lower frequencies where the distortion might be much worse. Or an amplifier's maximum output power is given, but its distortion was spec'd at a much lower level, such as 1 watt. Even when useful data is included, it's sometimes graphed at low resolution to hide the true performance. For example, a common technique when displaying loudspeaker response applies smoothing, also called averaging. Smoothing reduces the frequency resolution of a graph, and it's justified in some situations. But for loudspeakers, you really do want to know the full extent of the peaks and nulls. This measurement of a loudspeaker's response in a small room shows two different amounts of averaging. As you can see, third octave averaging hides most of the detail. Another trick is to format a graph using large vertical divisions, so the response looks reasonably flat, yet a closer examination shows that each vertical division represents a large dB change. I measured this loudspeaker in a fairly large room with a precision microphone about a foot away. This graph shows the measured loudspeaker response at high resolution. This graph shows the same data, but with third octave smoothing applied. And this graph shows the same smoothed data as before, but at 20 dB per vertical division instead of 5 dB. Which version looks more like what manufacturers publish? Now let's talk about measuring fidelity. I love this review. The USB wire has a relaxed quality that fosters deep musical involvement. Yeah, for $700 it certainly should. Unfortunately, this graphic from a home theater magazine is all too common. Each of these metrics is based on one person's subjective impression as he listened to the subwoofer in his living room. Overhang refers to how long the speaker continued to output sound after the source stopped. But there are no numbers, so this data is meaningless. Further, people who understand acoustics know that some notes continue to ring longer than others, depending on the room dimensions and the key of the music. Neither of those is given either. Rather than dissect everything wrong with this graphic, let's look at how the fidelity of audio gear should be measured. We'll start with the simplest measurement, noise. Noise is easy to measure using a sensitive voltmeter, though the voltmeter must have a flat response over the entire audible range. The response of many inexpensive meters rolls off above 5 or 10 kHz, and many aren't sensitive enough to measure very small signals. It's simple to measure noise using a suitable voltmeter, but what's measured doesn't necessarily correlate to its audibility. Our ears are less sensitive to very low and very high frequencies when compared to the mid-range, and we're especially sensitive to frequencies in the range around 2 to 3 kHz. These are the famous Fletcher-Munson curves that show how loud various frequencies must be to sound the same volume. To compensate for our hearing, many measurements employ a concept known as weighting. This emphasizes frequencies where our ears are less sensitive, so noise measurements will correspond more closely to their perceived volume. The most common curve is A weighting, shown here. There's also B and C. Of all the parameters that affect audio fidelity, distortion is arguably the most damaging because it adds new frequencies not present in the source. In the old days before computers were common and affordable, harmonic distortion was measured with a dedicated hardware analyzer, such as this model by Hewlett-Packard. A harmonic distortion analyzer sends a pure sine wave through the device being tested. Here, pure means the sine wave contains only the single desired frequency with minimal harmonics and noise. Then, a notch filter tuned to that frequency is inserted between the device's output and the sensitive voltmeter. A notch filter removes a very narrow range of frequencies, so whatever remains is distortion and noise generated by the device being tested. This diagram shows the basic method. Intermodulation distortion, or IMD, is more damaging audibly than harmonic distortion because the added sum and difference frequencies aren't always related musically to the original frequencies. For example, if you play a two-note A major chord containing an A at 440 Hz and a C sharp at 277 Hz through a device that adds IM distortion, new sum and difference tones are created at 717 Hz and 163 Hz. 717 Hz is about halfway between an F and F sharp note, and 163 Hz is slightly below an E note. Neither of these frequencies are musical notes, so even at relatively low levels, they add an unpleasant, dissonant quality. Again, harmonic and intermodulation distortion are both caused by the same nonlinearity, so they're always present together. Further, when IM distortion is added to notes containing their own harmonics, which is typical for musical instruments, some indifference frequencies related to all of the harmonics are created, as well as for the fundamental frequencies. Intermodulation distortion is measured using 2 test tones instead of only one, and there are 2 methods. The ITU-R method shown here uses 19 kHz and 20 kHz at equal volume levels and measures the level of the 1 kHz difference tone that's generated. The SMPTE method instead sends 60 Hz and 7 kHz tones through the device being tested, with the 60 Hz sine wave 4 times louder than the 7 kHz sine wave. Professional audio analyzers are very expensive, but you can do many useful tests using only a Windows or Mac computer with a decent quality sound card and suitable software. I use the FFT tool in Sony SoundForge to analyze frequency response, noise, and distortion. For example, when I wanted to measure the distortion of an inexpensive sound card, I created a pure 1 kHz sine wave test signal. I played the tone through a high-quality sound card having known low distortion, then back into the budget sound card which recorded the tone. As you can see, a small amount of high-frequency distortion and noise above 2 kHz was added by the inexpensive sound card. But the added artifacts are all more than 100 dB softer than the sine wave, so they're unlikely to be heard. Earlier I mentioned that our ears are more or less sensitive at different frequencies, which dictates how loud noise and distortion artifacts must be to be heard. Another factor is the masking effect. Masking is an important principle because it affects how well we can hear one sound in the presence of another sound. If you stand next to a loud motorcycle, you won't hear someone talking softly 5 feet away. Masking is strongest when the loud and soft sounds have similar frequency ranges. So when playing an old Led Zeppelin cassette, you might hear the tape hiss during a bass solo, but not when the cymbals are prominent. Likewise, you'll easily hear a low-frequency AC power line hum when only a tambourine is playing, but maybe not during a timpani solo. Therefore, the frequency distribution of the artifacts added by a device affects its audibility due to both Fletcher-Munson as well as the frequencies present in each source. These days it's common to combine harmonic distortion, noise, and hum together into a single THD plus noise spec. This is expressed as either a percentage or number of dB below the device's maximum output level. If an amplifier adds 1% distortion, that amount can be stated as 40 dB below the original signal. A-weighting is usually applied because it improves the measurement, and that's fair as long as the use of A-weighting is stated. There's nothing wrong with combining noise and distortion into a single figure when their sum is safely below the threshold of audibility. But when distortion artifacts are loud enough to be audible, it can be useful to know their specific makeup. For example, low-frequency artifacts are less objectionable than higher frequencies, and distortion at frequencies around 2 to 3 kHz are noticed more compared to harmonics at other frequencies. Again, this is why A-weighting is usually applied to noise and distortion measurements, and why using weighting is not unfair. This brings us to audio transparency. As we've seen, the main reason to measure audio gear is to learn if a device is good enough to sound transparent. All transparent devices, by definition, sound the same because they don't change the sound enough to be noticed, even when listening carefully. But devices that add audible distortion can sound different, even when the total measured amounts are the same. A-weighting helps relate what's measured to what we hear, but some types of distortion are more objectionable, or even more pleasing than others. For example, harmonic distortion is considered musical, where IM distortion is not. But what if you prefer the sound of audio gear that's intentionally colored? Adding color in the form of distortion and EQ is proper and valuable when recording and mixing. During the creative process, anything goes, and if it sounds good, then it is good. But a playback system should strive for transparency, whether it's the monitors in a professional recording studio or the hi-fi speakers in your living room. Recording engineers need accurate monitoring to know how the recording really sounds, including any coloration added intentionally. But with a consumer system, you should hear exactly what the producers and mix engineers heard. You'll enjoy their artistic intent only if your own system adds no further coloration of its own. But is transparent good enough? Even if a device is audibly transparent, that doesn't necessarily mean it's good enough, or that there's no benefit from even better performance. Audio typically passes through many devices in its long journey from the studio microphones to a consumer's loudspeakers. And what we eventually hear is the sum of degradation from all the devices combined. Not just distortion and noise, but also frequency response errors. When audio passes through 5 devices in a row that each have a modest 1 dB loss at 20 kHz, the net response is 5 dB down at 20 kHz. I reject the notion that the standard metrics for harmonic and IM distortion are irrelevant, as is sometimes claimed. Yes, a single number is not useful, and masking doesn't hide higher-order artifacts farther away from the source frequencies, so it's important to know all the measurement details. But the arguments I've seen that dismiss normal distortion tests are not compelling to me because they use contrived distortions, such as shown here, that don't occur naturally in audio circuits. As explained earlier, most audio circuits distort via 2 basic mechanisms: clipping at the peaks, both abrupt and gradual, and crossover distortion. Crossover distortion also occurs with analog tape due to a magnetic effect called hysteresis. To my way of thinking, distortion is more about the audibility of artifacts, regardless of their type or cause. If the sum of all artifacts is 80 dB or more below the music, which is common for modern electronic gear, the distortion won't be heard regardless of its makeup. 40 years ago, when 1 to 5% distortion was common, especially with tube gear, the nature of the distortion really did matter. Some distortions have a buzzy sound, and others are more thick and grainy. But these days, other than loudspeakers and microphones, audio devices are mostly transparent, so the specific nature of the distortion and its frequencies is irrelevant. Soft clipping, hard clipping, high order harmonics or low order, it just doesn't matter as long as it's all too quiet to hear. Well, that's certainly enough from me for now. Let's hear from some of the other panelists.
When I was working for a living, one of the things that I was doing was writing specifications for buying stuff. What I learned from that was that a specification isn't what you see in the marketing materials where they list all these various parameters and put numbers to them. A specification is something that the designers use. When a product is designed, they get together and they say, here's what we want it to do. We want it to have less than this % distortion. We want it to have that much maximum output level. And when they design the product, they test the product against the specification. Then it goes to the marketing department, and the marketing department makes up the spec sheets that are put in the manuals and put in the ad copy and put on the websites. But those are not really specifications. If you're lucky, it's test data, performance and tests. They conduct a test. They don't necessarily tell you what test they did, how they measured THD, for example, but they tested it, they got a number, and that's what we see. This can be useful data, but you need to know how it was measured, and you need to believe that was a legitimate way to measure it for your application. I cobbled up a little demonstration here. I set up a chain and calibrated it so that at nominal level, I had 5% THD as measured on an NTI minilizer. I had 2 kinds of distortion. One was clipping, just generated by driving the preamp a little hard. And the other was crossover distortion, generated by a little circuit. And I also had pictures, I think, of the spectrum of each one with a sine wave. And so even though numerically they both read the same amount of distortion, and 5% distortion's a lot, and this is a contrived experiment so that you're guaranteed to hear a difference, you'll notice that the crossover distortion sounds really broken. And the clipping is, yeah, it's distorted, but it's not so bad.
My background is mostly in microphones, so I was going to talk a little bit about some of the things that you see on microphone data sheets which don't really match reality all that much. This is an actual data sheet from an actual product. It's really totally content-free. It tells you about what the high-pass filter built into it is, but that doesn't have necessarily a connection with the actual response of the microphone, because that's combined with whatever the capsule response is. And then it tells you the frequency response is 20 hertz to 20 kilohertz, but it doesn't tell you how far up or down it is at those extremes. And traditionally, you talk about ranges when you do response plots like that. You think about plus or minus 3 dB on it either side. But clearly, if there's a high-pass filter that drops 6 dB at 150 hertz, then it's going to be more than 3 dB down at 20 hertz. So that number probably is maybe plus and minus 40 dB or so. Who knows? It requires a dedicated power supply, but it doesn't say what kind of power supply or how much power it takes or anything. And that output impedance is also fake. As far as polar pattern goes, the thing about microphone polar patterns is they change with frequency, and they change aggressively with frequency. And just saying it's a cardioid microphone doesn't tell you all that much, because there are a bunch of cardioids that are secretly hypercardioids at some frequency. And they all turn into omnis at low frequency anyway. So you can't just put one pattern, you actually have to have a reasonable plot. So I guess we have max SPL size and weight. Those are real numbers. This is actually the same microphone sold by a different vendor, but it's made in the same factory in China. So this is a different data sheet from a different manufacturer. Now, this does actually have frequency response plots on it. But you'll notice the frequency response plot on this, at 180 degrees, it has more high frequency response than it does at 0 degrees. They've actually swapped the 0 and 180 plots on this, which is kind of interesting. Here's a different microphone from a different company altogether, but you'll notice exactly the same frequency response, and they've still swapped the two. And the answer is that these companies are selling microphones that have a capsule that's made by a particular factory in China, and they got the capsule response, and they put it on their data sheet. The actual response of the microphone is a combination of the grill and the electronics and the capsule, but what you see here is the capsule response.
Now let's consider some other important audio specs. Frequency response, noise, and distortion are the most common audio specs, and they're arguably the most important, but there are other specs that I'll touch on briefly. First up is impedance. The input impedance of a circuit determines how much of a load it presents to the device driving it. If we use the analogy of levers and springs, a high impedance is like a loose spring that compresses easily, and a low impedance requires more effort to move. This graphic could be shown as a simple downward force on the spring, but I added a lever to show how a transformer affects the ratio between distance and torque, which is the same as voltage versus current. Moving the pivot along the length of the lever varies the ratio of input to output impedance. Years ago, when the audio industry was concerned mainly with telephone systems, devices were connected using a method called impedance matching. Audio equipment had an input and output impedance of 600 ohms, which transfers the maximum amount of power from one device to another. Modern line-level audio circuits use a better method known as bridging, where outputs have a low source impedance and inputs have a high load impedance. This method allows driving long wires without loss due to wire resistance, and also lets one output drive many inputs at once without distortion. A typical line-level output impedance is less than 100 ohms, often much less, and inputs are generally around 10,000 ohms or greater. However, passive electric guitars and basses without built-in preamps for their magnetic pickups require a much higher load impedance. Acoustic instruments having a piezo pickup require an even higher load impedance. Instrument amplifiers and DI boxes usually have an input impedance around 1 megohm or 1 million ohms, and preamps used with piezo pickups can be even higher. If you feed a passive instrument into a lower impedance, the frequency response suffers. So if you plan to record an electric bass directly without a microphone, input impedance is an important spec when comparing, for example, USB sound cards having both XLR and quarter-inch inputs. I'd say that 500,000 ohms is a reasonable minimum for an instrument input. Wires are low-tech, but they can definitely affect fidelity if they're poorly made or inappropriate for the task. For example, wires that are poorly soldered or crimped can become intermittent or even add distortion as the marginal connection acts like a diode passing AC signals more in one direction than the other. The two most important properties of a wire are its series resistance and parallel capacitance. For line-level signal wires used in a bridging connection, resistance is not a factor. But too much capacitance can lose high frequencies, especially if the driving source impedance is high, which creates a low-pass filter at audio frequencies. Resistance is important with speaker wires where power is transferred, so for longer lengths, it's important to use wire thick enough for the amount of current it will handle. Wires also have series inductance, which could affect frequency response, but that's not an issue at audio frequencies. For power amplifiers, the available output power is as important as anything else. Not only the amount of raw power, but also how that power transfers to the loudspeaker. There are two ways to specify power, continuous and peak. Both are important, but the amount of power that can be delivered continuously matters more. An amplifier might be able to provide a short burst of several hundred watts for a few milliseconds, but unable to output even half that amount continuously. So a brief snare hit might get through undistorted, but not a sustained bass note. Years ago, it was common for amplifier makers to list only peak power output in their advertisements, and some of the claims bordered on fraud. For example, an amplifier that could output only 30 watts continuously might claim a peak power output of hundreds of watts, even if it could provide that much power for only 1 millisecond. Thankfully, the U.S. Federal Trade Commission passed a law in 1974, making this practice illegal. A power amplifier has two output limitations: available voltage and available current. An amplifier might be able to provide its full rated power into a 2-ohm loudspeaker, but only half that into 8 ohms, or vice versa. For a given output voltage, a lower impedance draws more current from the amplifier. If an amplifier is unable to supply enough current, the result is distortion, even at levels well below the amplifier's maximum rated power output. Many amplifiers sold to the pro audio market can drive 2 ohms, which yields more power than into 8 ohms for a given output voltage. Most loudspeakers have a stated impedance of 8 ohms, but many are much lower at some frequencies. This speaker driver is rated at 8 ohms, yet you can see that the impedance is less than 8 ohms for the range between 100 Hz and 3.5 kHz. Some loudspeaker systems rated at 8 ohms fall as low as 3 ohms or even lower at some frequencies. More output current is needed to drive a low impedance without distorting, compared to a high impedance which presents less of a load. Another spec related to power amplifiers and loudspeaker impedance is damping factor, which is the ratio between the amplifier's own output impedance and the speaker's input impedance. As you probably know, a dynamic loudspeaker can serve as a microphone, and vice versa. Damping is the ability of an amplifier to absorb voltage fed back to it from the loudspeaker. When an amplifier sends voltage to a speaker and then stops sending that voltage, the cone continues to vibrate due to inertia. This generates a voltage called back EMF that's sent back to the driving amplifier. If you've ever used a hand-cranked generator, you know that the handle turns easily with no load connected, but is much more difficult to move with a load. Likewise, a power amplifier's very low output impedance can halt or damp the continued vibration by presenting a very low impedance to the loudspeaker when the loudspeaker acts as a source. So a high damping factor is better, though the resistance of the speaker's own voice coil limits damping factor to around 50. Power amplifiers sometimes claim impossibly high values, in the hundreds, but that's really just marketing because such high values are never achieved in practice. Slew rate describes how quickly a device's output voltage can change, and it's expressed in volts per microsecond. This is different from frequency response, which is independent of output voltage. If a power amplifier is 3 dB down at 50 kHz, it will be reduced that much whether the signal is 1/10 of a volt or 10 volts. However, a circuit's maximum output at high frequencies is limited by its high-frequency response and also by its slew rate. A preamp might be flat to 50 kHz when passing small signals, but unable to output even 10 kHz at high levels without distortion. As you can see, some parts of a sine wave change voltage more quickly than others. When a circuit goes into slew rate limiting, its output is unable to keep up with its input. This changes the wave shape, which adds distortion. For reference, if a circuit has a slew rate of 1 volt per microsecond, it can output about 10 volts peak to peak at 20 kHz without adding slew rate-induced distortion. Earlier I mentioned wow with phonograph records, flutter from analog tape recorders, and jitter with digital devices. All three of these are timing errors. Since this is the 21st century, I'll skip the first two and address only jitter. Where wow and flutter modulate the pitch of the music higher and lower, jitter manifests as FM sidebands. These are noise-like artifacts that are added to the music. Depending on the nature of the jitter and its cause, the sidebands may be harmonically related or unrelated to the music. So jitter might manifest more as noise or more as distortion. Either way, jitter audibility depends on both the loudness of the artifacts and the masking effect mentioned earlier. Of course, jitter artifacts show up in the standard distortion test anyway. As you can see in this graph, the noise spectrum of jitter rises at higher frequencies. You can see that the noise from jitter less than about 1 nanosecond is softer than the noise floor of a CD at most frequencies. We've all heard tape hiss many times, but I've never heard hiss from a CD. So 1 nanosecond seems low enough to be confident that the jitter won't be audible. For reference, the jitter from my Focusrite Scarlett 8i6 USB sound card is spec'd at less than 1/2 nanosecond. The 8i6 is a mid-level prosumer device that costs $250. Aliasing is another artifact related to digital audio, but it's too soft to hear in modern devices. Aliasing is similar to IM distortion because new sum and difference frequencies are created that may not be related musically to the source. In this case, one source frequency is the incoming audio, and the other is the sample rate. All digital converters include steep filters to remove frequencies higher than half the sample rate, which avoids aliasing. There are a few other miscellaneous specs also worth mentioning. EIN stands for Equivalent Input Noise, and this spec applies mainly to microphone preamps. All electronic circuits generate noise. Even a resistor, which is a passive device, generates some amount of noise that can be calculated based on its resistance in ohms and the ambient temperature. This noise is called thermal noise, or Johnson noise, after J.B. Johnson, who discovered it in the 1920s. Thermal noise exists at temperatures above absolute zero and is caused by random molecular motion. Assuming a room temperature of 70 degrees Fahrenheit, the theoretical lowest noise possible is around -131 dBu when considering only the audible range. Therefore, an EIN spec should include the bandwidth being considered and whether A weighting was applied. Another spec that relates mainly to preamps is maximum gain. Most condenser microphones output fairly large signals, some even near line level. But passive dynamic mics output only a few millivolts, and passive ribbon mics output even smaller signals. So a preamp should offer at least 50 or 60 dB of gain for use with dynamic mics, and 80 dB is not uncommon for preamps that accommodate ribbon microphones. Crosstalk, or channel separation, or channel leakage, is spec'd in dB, and it states how much sound from the left channel ends up on the right, and vice versa. Crosstalk is rarely a problem with audio hardware, and it's not an issue at all with audio software. As with distortion, masking helps hide small amounts of leakage from one channel to the other, so this is one spec you can usually ignore. For perspective, Analog tape recorders struggle to achieve 60 dB at mid-range frequencies, and the very best phonograph systems can barely achieve 40 dB. At higher and lower frequencies, the crosstalk from these mediums is generally much worse. Channel balance is also not usually a problem, though it can be. Anyone serious about audio should calibrate the channel balance throughout their system, and especially at the loudspeaker outputs, to ensure that content panned to the center emits from both speakers at the same volume. This is never a problem with software, though cheap analog volume control pots can shift the image left or right at low volume settings. The last two specs I'll cover are related: maximum input level and maximum output level. Some devices distort when sent large signals, even if their input volume is turned down. If a mic preamp can't handle a high-output condenser microphone placed close to a loud sound source, you'll need to insert a pad inline to attenuate the signal. Maximum output level affects headroom, which is the difference between the average and peak volumes. Headroom is important in an all-analog studio, but with modern computer-based setups, it's rare for a sound card's output level to be insufficient. You simply set the volume controls so 0 dB full scale from the converter is a reasonable level for whatever device follows. Finally, I'd like to mention something I do appreciate about One Hi-Fi Magazine's reviews. While Stereophile focuses mainly on subjective impressions, they also include test data their editor John Atkinson measures. In my opinion, this is much better than simply parroting a vendor's specs. Stereophile also lists every reviewer's other equipment. I think this is useful because it lets us assess the reviewers themselves to see what choices they made for their own systems, including whether or not they have acoustic treatment. Speaking of acoustic treatment, I'll mention briefly how acoustic products are tested. Unlike measuring electronic gear, which is straightforward, test methods for bass traps and other acoustic products are less clear. First, understand that all materials simultaneously absorb, reflect, and pass through. If you put an absorber panel made of rigid fiberglass or acoustic foam on a wall, very low frequencies will pass through to the wall and then reflect back. But at very high frequencies, some of the sound may reflect back from the front of the absorber itself, especially with higher density materials. The basic unit of absorption is the Sabin, named for Wallace Clement Sabine, an early American acoustics pioneer who developed the concept of reverb decay times. The Sabin is an absolute measure of absorption, so a large panel absorbs more than a small panel. But absorbers can also be spec'd by their absorption coefficient, which is like a percentage. Packing foam, which is not useful for acoustics, absorbs less than 50% of the sound at mid-range frequencies, and even less at higher and lower frequencies. Absorbers meant for music rooms absorb 100% at mid and high frequencies, with less absorption at low frequencies. How low the absorption extends to depends mainly on its thickness. Owens Corning 703 rigid fiberglass 4 inches thick absorbs 100% to below 200 Hz when placed flat on a wall, and even lower when spaced away from the wall. But thin panels are much less effective at low frequencies. The most common acoustic problems are peaks and nulls, comb filtering, flutter echo, and modal ringing at bass frequencies. All of these can be solved using absorption, though many studios and listening rooms also employ diffusion. Diffusion scatters sound waves in different directions rather than absorbing them. This avoids the problems caused by reflections from nearby surfaces, but without reducing the acoustic energy in the room as much as absorption does. Where absorbers are 100% effective down to a given low-frequency roll-off, diffusers are more effective at mid-range frequencies. For a QRD diffuser like this, the depth of its wells determines how low the diffusion extends to. The well width dictates its highest effective frequency. A complete discussion of how acoustic treatment is tested goes far beyond what I can present here, but I want to explain why some acoustic specs are less useful than we'd like. In the US, 1 Sabin of absorption is equal to a 1 square foot opening to the outdoors. So an open window that's 2 by 2 feet has an absorption of 4 Sabins because the open area is 4 square feet. All of the sound reaching the opening passes through to the outside, and none is reflected back. Again, the Sabin is an absolute amount rather than a percentage, so a large opening absorbs more than a small opening. The problem with absorption coefficients is they're dimensionless. A very small absorber can claim performance identical to a larger product that performs much better. Another problem is the test methods themselves. The vast majority of acoustic absorbers are not sold to the audio industry. Rather, most testing evaluates mundane products such as office ceiling tiles and automobile interiors. The standard method defined by the ASTM places at least 60 square feet of material on the floor of a highly reverberant room, with only the top surface of the material exposed. The room's reverb time is then measured at the standard third octave frequencies with and without the material present. Absorption is calculated based on how much the reverb times were reduced in each band. But absorbers meant for audio and music are often placed straddling corners for bass trapping, or mounted away from the wall or ceiling, allowing the rear surface to also absorb. As you can see, it's impossible to orient multiple corner-shaped absorbers so only their front surface is exposed. A similar problem exists with exposed panel edges. As you can see, the edges of a panel 4 inches thick add fully 50% to the total absorbing surface. Many commercial absorbers are built this way intentionally, with the edges exposed. So for panels having exposed edges, placing them adjacent with the edges blocked, as the ASTM standard requires, unfairly reduces the measured absorption. If you're interested in learning more about how acoustic products are tested, my article from Sound and Vibration magazine is available on the Real Traps website, also linked in the description for this video. Well, that wraps it up. Thanks very much for watching.